We'll see if I can post this one later on. So, the smart dust supposition that I've put out there, we've got some new learning to do. Somebody dropped off this about Darpa's newest release, More Than Microchips, episode 85. And January 31st, 2025, when I played Darpa TV recently, I brought this up. Darpa's Microsystems Technology Office, okay? Microelectronics are the foundation of technology today, but what about tomorrow, 10 years from now, and 20? January 31st, 2025. Real breakthroughs don't come from simply refining what already exists. They come from reimagining what's possible. In this episode, Dr. Whitney Mason, director of Darpa's Microsystems Technology Office. Microsystems, MEMS, very large-scale integration, NFT, tokenized economy, molecular communication. Just to refresh some memory, because oh, the acronyms. Like the Micro Machine Man, micromechanical engineered systems refers to devices or systems that combine tiny, very, very small, like nano micrometer scale small, tiny mechanical components with electrical engineering beam steering circuitry. Air molecules that are used as circuits. It's called visible light communication. It's called free space optical. Essentially meaning micro electromechanical systems, MEMS. These are miniature machines fabricated using integrated circuit techniques, allowing for complex functionalities on a very small scale, often with dimensions ranging from millimeters to micrometers. Yeah. And so most of the time, when I say smart dust, people are thinking way too large, okay? So, yeah. MEMS incorporate elements like tiny gears, levers, beams, and actuators integrated with microelectronics to sense and respond to physical stimuli. Typically produced using semiconductor fabrication techniques allowing for high precision and large-scale production. MEMS are used in a wide range of applications, including accelerometers in smartphones, pressure sensors, gyroscopes, inkjet printer heads, microfluidic devices, and tiny medical implants. I'm going to show you exactly where they connect to biosensors here in a bit, because whenever I come this direction, we're not thinking air molecules, we're thinking this stuff, which is another component of what they do. But when I say this stuff, I'm, at least for me, I would be thinking microchip, okay? So hold up. Boy, you're gonna love this. Electronics for you in ways that you probably didn't want them to. If I can get the glitter off of there. There we go. So heterogeneous 3D integration technology, you see up here where it says microfluidics and nanostructure, okay? Biosensor, analog front end, digital post-processing memory, okay? So there's biocomputing reasons for this. There are smart, what do you call it? Your metamaterials, software-defined metamaterial routing for this. There's the terahertz changes like we see in the video for all the substrates and topology that they change on the top of their smart dust. Heterogeneous and monolithic 3D integration technology for mixed signal integrated circuits. Sensor, analog radio frequency, digital logic, and silicon substrate, I believe, SI. Okay. So then besides the biocomputing and besides the quantum computing, there's also the air molecules, okay? Where did I get this? This is 3D heterogeneous integration. You know where I got it? Welcome back to Darpa. So, I'll take you there in just a second. Here's our smart dust MEMS that are flowing in beam-steered circuits through the air. Okay, through the air. And that's what a lot of the magnetics and the pushing and the pulling and all these radar systems help keep in check. So, she explores the potential of organic circuits. This is also your organoids and organelles because they're controlling the particulate of the atmosphere. Okay? Organic circuits to revolutionize computing, not by replacing existing tech, but by opening entirely new frontiers in electronics design, from assessing the potential of quantum computing to novel material innovations. There's your metamaterials. Anytime they say novel, they mean emerging. For how long? Could be 30 years. Emerging. Novel material innovations that could redefine performance and efficiency. Microelectronics Technology Office with Darpa is driving advancements that go far beyond conventional chip making. Dr. Mason also shares perspective on how DARPA's risk-taking culture enables groundbreaking discoveries and why the speed of innovation is critical to maintaining U.S. technological advantage. She discusses MTO's focus on next-generation manufacturing approaches that integrate the best-of-breed materials to achieve disruptive performance leaps. By moving beyond traditional microelectronics and embracing unconventional ideas. Microsystems Technology Office is working to create the future of technology where microelectronics aren't just smaller and faster, but smarter, more resilient, and capable of things we have yet to fully envision. So me being me, I'm like, what's all that over there? Next generation microelectronics manufacturing, okay? So what's all that about, right? The Next Gen Microelectronics Manufacturing Program, known as NGMM, aims to unlock accessible prototyping for the microelectronics of tomorrow by establishing the first ever National Center for Advancing United States-based 3D heterogeneous integration. And that is where I wound up here with all the different stratas that I already know, how you're using your integrated circuits with and without the nano. Okay, I understand because of the synthetic biology and all the routing crazy going on between hybridized or augmented people, as well as robots, self-driving cars, and logistics. See, when we say human hybrids, everybody goes, but when I say self-driving cars, you go, oh. When I say smart city, you go, oh. Okay, microfluidics. Why do you sound so annoyed? Because this is another place where here on the channel, when I show you this a picture, you're going to be like, oh, that again. Yeah, that thing where they log into your body via your skin or your intranasal and they start changing your cell structure around with their little steerable machines, robots, and the help of some infrasound that is contained in your veins and arteries via the interbody area network on software-defined networking on the physical logical layer that is the human skin, wandering around the free space optical with the spine tree, reaching out to network function digitally with Cisco digital network architecture, reach out and touch a human. Not a problem. Kind of biosurveillance, national biosecurity. What are we looking at? Microfluidics and the digital twin. Why are we talking about microfluidics with 3D heterogeneous integration? Computers that you're moving with your mind, just like the drones. Oh, or a computer, okay? We could be using a logical controller. Sorry for my screeching on the desk, I gotta fix that. So these different integrations and chipsets, you guys left out your organelles and organoids in the atmosphere, the quantum computing you're already doing, okay? And you're already 3D printing for yourselves in autonomous laboratories with the proteins and the protein folding. for each other, okay? So now we've got a whole new integrated circuit situation going on with the different types of nanostructures, microfluidics, but then different ways to actuate those structures and different ways to hide or modulate the signal. Lovely. What do we call it? 3D heterogeneous integration for all your different circuit dynamics that you're playing with for the quantum integration of the atmosphere. See, if the Department of Transportation is already pushing V to X, which is your augmented reality, as well as the particulate in the atmosphere being malleable in exactly the beam steering missile defense kind of way, then the rest of you, 3D heterogeneous integration photonics, how about that? Why don't we open up that search quick, okay? Will that make it easier for you to start admitting that you're beam steering all this stuff as a matter of photonics and nanomedicine? Would that be more helpful? A technology where different types of photonic components like optical waveguides and electronic circuits. What is a photonic component? Photonic components are those in which light photons are generated, controlled, and detected, analogous to electronic components processing of electrons. A photonic component, a device that generates, manipulates, or detects light, photons, light, like biological photons, light, essentially acting as electronic components, but using light instead of electrons to process information. Examples include, examples of what? A photonic component, lasers, optical amplifiers, waveguides, modulators, photodetectors, all of which are used in fields like telecommunications and healthcare, where high-speed data transmission is crucial. Yeah, and so then they see chip, photonic integrated circuit, and they're thinking, oh, well, see, the photonic integrated circuit, it's a chip on a board somewhere, right? Steering air molecules around. Oh, that's HVAC normal since the 40s. Yeah, we don't like to talk about photonics because it's part of the hidden Cold War science crew. That's what I'm going to start calling it, because that is what it is. Anything that has to do with optics, light, oscillation, frequency, and sound, you guys hit that. So for me, I'm like, oh boy, integrated circuits all over with these smart materials that are getting more metamaterial friendly, more topology with your quantum dot friendly for a single photon with a silicon waveguide. So here's your quantum dots, and we are at the single photon level. Now here's the problem I have. You guys out there don't admit to biophotons. What is a biophoton? They do, you don't. Low energy photon of light emitted by living organisms. A type of bioluminescence. Biophotons are produced by all living things, including humans. Oh, yeah, we're at it again. And what will be told, or at least me, I get yelled at all the time, there's no electrons, there's no photons, there's nothing. There are no cells, these people go to great lengths to ensure that there is absolutely no intellectual discourse whatsoever. What do you see there? Oh, it's more Curlian photography. Yeah, that's semantics, scholar, and let's see what it says. Biophoton research. Gotta fix that. But, maybe it'll get like nails on a chalkboard for you too, to sit there and play stupid that your body is not electrical. Because that's what we're doing, okay? And they're not using a new technology. They're using your bioelectricity and your legit biophotons, light stored within your DNA. Yeah, good job. So they're into the mitochondria. They're using our molecular communication. They're using our body as their little antenna. They're using our DNA for data storage. They're using our bodies to route their data with our red blood cells. And you can't even be bothered as a material physics person or just a human, anybody, to admit that your body's electrical. See where the problem is? The emperor has no biofield. And no matter how many ways we go through this, they're just going to work and improving the circuitry they have Lithium niobate integrated photonics. There goes the Tory community eye rolling going, we know all about lithium niobate and all that kind of stuff. Yeah, because they're using these things. And when you see a big old, chipset, again, like this, you're not thinking air particulate creating a topology exactly like this in the air molecules around you. Why would you be? But they are, since the 70s. Okay? So, let me open up really quick. Where did you go? Oh, come on now. Here we go. Let me open this one up. You reading that? It's a new Moore's Law-like scaling curve in November of 2023. In a previous post, we dove into Moore's Law for integrated circuits and outlined general scaling principles that we use to seek out systems that can scale in ways that resemble Moore's Law in terms of decades of scalability, which results in orders of magnitude of increased performance and capability. In this post, we will introduce an emerging platform in photonic integrated circuits and describe how its scaling curve can resemble Moore's Law. Photonics, in the form of fiber optics, has been used for many years to transmit data at high bandwidth over long distances. However, as the demand for interconnect bandwidth has scaled in recent years due to increased data-intensive internet traffic, i.e. video streaming, and new applications such as AI, it is becoming necessary to increase the interconnect bandwidth in a more scalable manner than traditional electrical interconnects and photonics components will allow. Over the last 20 years, photonic integrated circuits, or integrated optical waveguides and components on a chip, have emerged as scalable optical analog to electrical integrated circuits. You want to talk about your dark fiber? It's the Internet of Space things, with free space optical, with optical body area networks. You want to talk about them? Right. Have emerged as a scalable optical analog to electrical integrated circuits, primarily to address the issue of data movement bottlenecks in compute systems. While their development and adoption have been slow, we believe we are on the cusp of a new Moore's Law type scaling curve that can enable not only decades of interconnect bandwidth scaling, but additional broader impact across computing and sensing industries. You ignore market share at your own peril, I guarantee it. In ways that will be difficult to anticipate. The rest of this blog post in 2023 will be dedicated to uncovering scaling principles in photonics and how they can enable decades of technology scaling through innovating and maturing new materials, processes, and designs. Lasers, modulators, resonators, more integrated on a single chip. To start, the most basic advantage of photonics over electronics is that data can be transmitted over long distances independent of data bit rate, resulting in low energy per bit data transmission. In electronics, the distance that data can be transmitted is inversely proportional to the bit rate of the transmitted data, as shown in the figure below. This means that as the bandwidth of the interconnect increases, the distance that the data can be transmitted decreases for a given power. This fundamental difference between optics and electronics boils down to the fact that metal wires have capacitance, while optical fibers do not. Electrical signals propagating in interconnects require charging and discharging of those metal wires, resulting in unwanted power consumption and waste heat. With demand for interconnect bandwidth in data centers doubling roughly every 2 years, the trade-off between bandwidth and reach of electrical interconnects will eventually become unsustainable, forcing the adoption of photonic interconnects at lower and lower levels of the stack. Ever heard of a bit rate before? I hope so. Photonics also has other distinct advantages over electronics, which can be exploited for high bandwidth, low power, and low cost data transmission. Well, there's your wavelength division multiplexing. Single optical fiber can transmit data at high data rates over hundreds of wavelengths. To expand link bandwidth, light transmitted in fibers or waveguides do not dissipate power in the form of heat. Coherent light, think lasers, exhibit wave properties like interference, which can be used to encode data and transform data in unique ways. When evaluating the performance of photonic integrated circuit, like in compute, the most critical metrics are analogous to the power, performance, and area metrics that we observe in processors. In the case of interconnect, PIC's performance and area are summarized by bandwidth, and power is usually described in terms of energy per bit transmitted received. Current pluggable optics solutions can achieve bandwidth densities around need link and energy per bit around 15 something joules per bit. As we evaluate how photonic integrated circuits can scale these parameters by orders of magnitude to achieve greater than 10 terabits per second, assume millimeter BW. I need to look at you. Oh dear Lord. I didn't guess millions, terabits and scale. That's why I didn't want to qualify PJ per bit. All right, let's take a look. I want to know. Power efficient, yeah, understood. But short reach die-to-die links. Oh, okay. All right, so using PJ/bit, how much energy it takes to fetch one bit from the memory and then multiply it by the total amount of data you want to fetch. Okay. And then U. I figured that's what it was. So, yeah, heterogeneous integration is a cost-effective solution to increase the performance of system on a chip by taking advantage of the most appropriate process technology for each functional block that makes up a system. However, to operate efficiently, high bandwidth interconnects are required, and RDL comes as a cost-effective solution. Fine pitch demands. Redistribution layer. In advanced semiconductor packaging, where very narrow, closely spaced copper traces are created using a damascene manufacturing process. I don't know how that's pronounced for you guys. Allowing for high-density interconnects with extremely fine pitches. Small distances between the traces, like pitches on a roof. Enabling high-performance compact chip designs, particularly in 3D stacking and fan-out wafer-level packaging. Yep. Quantum and semiconductors. Semiconductor engineering, manufacturing, packaging, and materials. Somebody's blog. The needs of high-performance devices for AI high-performance computing. Data centers. Data center applications have drastically accelerated during COVID. At the same time, the integrated circuit industry struggles to minimize the silicon technology node to satisfy the endless requirements of computing performance. Like I said, quantum, in the air, underground, all over, all around. Yeah, because none of this is new. And all of this is circulating around the same anatomy that emits bioelectricity and biophotons. Yeah. And they're logging in and out of that anatomy. Yep, and they call it a body area network because it's their network to play with, because everybody's mouths are glued shut about all of these different, very powerful systems that are well past Moore's Law problems. And the NSA is ahead of you all, like normal, with Darpa, okay, and IARPA and BARDA and your JSON group and all this kind of stuff. And so I've been trying to get to photonics here on the channel. All right, I'm coming up on 30 minutes and I don't want to go too much further at the moment, because what I want you to understand is that they're using weaponized air molecules, okay? They're beam steering through the air. They're not using anything less than your own bioelectricity and the molecules around you. So, given the agency's expectation that future innovation hinges on the fusion of diverse materials, devices, and circuits through advanced packaging, 3D-HI, 3D heterogeneous integration, will be key to U.S. technological leadership. Establish a self-sustaining manufacturing center for R&D and pilot production of high-performance 3D-HI microelectronics, currently working with the University of Texas at Austin, existing Texas Institute for Electronics Research Center. Low volume production. The center will leverage partnerships spanning organizations, defense industrial base, domestic foundries, vendors and startups, designers and manufacturers, members of academia, other stakeholders, to achieve a shared vision for national and economic security. The center encompasses both a physical locale and a research pipeline to drive dual-use innovations, supporting the defense sector, academia, and industry. Developments of 3D HI technologies creates the ability to stack separately manufactured components, chips, or wafers originating in different facilities, containing different semiconductors and materials within a single package. In realizing 3D HI microelectronics that incorporate diverse materials beyond silicon, NGMM focuses on revolutionary improvements in functionality and performance. Moreover, these advances provide an opportunity for U.S. leadership in cutting-edge microelectronics of the future. Phase 0 of NGMM conducted in 2023. Performer teams work to define, analyze, etc. Phase 1 and 2 are 2.5 years in length. Phase 1 awarded in July 2024, establishing infrastructure basic capabilities. Kickoff for Phase 1 took place in September 2024. And NGMM is a cornerstone of ERI 2.0, a Darpa initiative to ensure domestic leadership in cross-functional, future-focused microelectronics research. What are you? We just need to go to Darpa TV, y'all. The Electronics Resurgence Initiative, DARPA's response to national-level microelectronics concerns, is designed to ensure U.S. leadership in cross-functional next-gen microelectronics research, deployment, development and manufacturing, not deployment. The initiative aimed at both national security capabilities and commercial economic competitiveness and sustainability, so we're already deployed, as a thematic portfolio. I know that we are, but I want to read it right. Thematic portfolio of research programs primarily in the Microsystems Technology Office. That's why I figured I'd take you there. These programs emphasize forward-looking partnerships with U.S. industry, the defense industrial base, and university researchers. ERI's focus with the announcement of ERI 2.0, which seeks to reinvent domestic microelectronics manufacturing. Oh, so we're going to make more smart dust. Of course we are. Silly me. Yeah, 2021. Archives, slides, videos, agendas. Yeah, as usual. Oh, we just have no idea. My precious babies are so stupid. Making so much money. Okay. Hey, this is Agenda 2030, C40 cities. This is your electronic corridors. This is you charging your e-cars. This is everything you've been asking for with the drone warfare, the 3009. They build themselves all these little reassembling smart dust materials, these little microelectronics. They are your grid system actuating itself to react in real time to get the job done, whether by weather particulate, smart dust in a geofence, or something completely different, like sending signals to send in search and rescue drones, alerts about water systems. It's a whole bunch of stuff. It's all using the same sets of systems as well. That's why I keep complaining about the missile defense side. So that's that's the end here of what I want to get into with microelectronics manufacturing. And I hope you'll stick around for the next video. Mark 5:36. Amen.